For my pre-doc project here, I've been working with Yanfei Jiang and Phil Armitage in the Planet Formation group. I've been attempting to model radiation transport in protoplanetary disks in order to investigate the effect, or the influence, I should say, of the resulting thermodynamic structure on planet formation. So to give some context, when a gravitationally unstable molecular cloud core collapses, conservation of net angular momentum will form a differentially rotating protoplanetary disk of gas and dust around the newly formed pre-main sequence host star or stars. And it's in this environment that submicron interstellar grains must grow at least 13 orders of magnitude in size to become fully formed planets. Now, at large scales, the gas maintains vertical hydrostatic equilibrium, but the dust, as these grains grow in size, they decouple from this gas and settle to the midplane. This leaves the atmosphere of the disk optically thin or transparent to stellar radiation, but the midplane optically thick or opaque. And it's the frequency-dependent opacities of these silicate grains that can result in a colder midplane and slower disk cooling times, both of which will affect the thermodynamic structure and properties of the disk, which in turn can influence the various stages of planet formation and migration. Now, in attempting to model this numerically, I'm using the Athena++ hydrodynamic grid code, which now includes a radiation transport module. Now, some features that make it useful for this particular investigation is that in solving the radiation transport equations, it doesn't make any extreme approximations. For example, it doesn't assume a diffusion dominator optically thick limit, nor does it treat the radiation field as another fluid. And it's been shown to be accurate from both optically thick to optically thin regimes, which is quite appropriate for the dynamic range and optical depth in protoplanetary disk environments. Furthermore, the code is efficient in solving for non-relativistic flows such as the gas that we find in protoplanetary disks, and it achieves this by iteratively and implicitly solving all the terms in the radiation transport equation to avoid limiting the time step by the speed of light. In addition, the code has been recently extended to allow an arbitrary number of frequency groups for both absorption and scattering opacities, which is useful for the opacity tables for silicate grains that we now have some constraints on from recent observations. Now, one important aspect of the code is that in solving the radiation transport equation, it solves the specific tensity simultaneously along discrete rays. So, for example, if we look at the volume center of a spherical polar grid cell in the simulation, the minimum number of angles in this case is 8, where in preserving symmetry, the angles in this case point roughly to the vertices of this cell, but in actuality, the algorithm to produce the number of discrete angles is such that it preserves, or sorry, I should say it makes the solid angles subtended by each of these rays equal to one another. And so as a result, we now must also consider the angular resolution of the simulation in addition to spatial resolution in order to balance accuracy against computational performance. Now, in some of my efforts to model these disks, we start with for example, a disk midplane profile, which typically is a simple power law, for example, in the top panel in density or in the bottom panel in temperature, although I have modified the density profile with a sigmoid near the inner boundary to avoid any sharp jumps or discontinuities in the extinction coefficient, which could yield sometimes numerical artifacts as the implicit solver tries to solve the field at that boundary. But the actual model is a 2D axisymmetric polar wedge, as shown by this middle plot here in this green color map representing the dust density. And the horizontal axis you can see is the polar angle in degrees, the horizontal axis being the radial distance from the star in astronomical units. And the vertical density profile of the dust is a Gaussian centered on the midplane. And we overplot a contour showing where the optical depth reaches unity assuming, in this case, the gray absorption and scattering capacities, which means that the values of these remain constant over all relevant wavelengths. Now, with this model, we can actually solve the radiation transport equation analytically in terms of optical depth if we assume purely radial stellar rays from a sun-like star to find what we expect the radial flux to be. And so you could see in this color map of yellow and blue of the radial flux that in the atmosphere, which is optically thin, the flux follows a inverse square law dependence. But in the optically thick midplane, once the radiation encounters an optical depth of 1, it drops substantially as far as 10 order magnitude or more deeper into the disk and further back toward the end. Now, in attempting to implement this into the Athena++ code, given the angular discretization, we have to be very careful in trying to model these incoming radial stellar rays at that inner boundary. And so the way we achieve this is within the ghost cells of the simulation that just lie within the inner boundary of the domain. If you have this, we look at this azimuthal slice of that cell, polar in the vertical and in the radial direction horizontally. You have a discrete set of angles with which the intensities can be solved along, and we only allow non-zero intensities that correspond to the expected stellar flux at that inner boundary along the rays that are closest to this radial direction, while leaving all the rest zero. And so, as a result, this has an effect on the results given this angular discretization. And so you can see here a comparison as we increase the number of polar angles in the simulation, how it affects the flux that we find. So at the lowest, or at a relatively low polar angle resolution of 16, you could see that these oblique rays that are, for example, coming upward from below the disk or downward from above will cast a shadow as it crosses the disk, leaving these penumbra above and below the disk. And these rays also, as it penetrates the midplane, can heat up that midplane. Whereas if you increase the angular resolution so that the rays become less oblique and more parallel to the radial direction, it reduces that penumbra and, in fact, makes the expected flux much lower in those midplane regions, especially toward the end. Now, of course, we're most interested in the thermodynamic structure, and so what we can do is we let the system evolve with passive heating in a hydrostatic way, meaning we disable any azimuthal gas velocities, and we do not allow any radiation source terms to go onto the gas. So, for example, momentum transfer from like radiation pressure. And so, as a function of time, if we look at, for example, the total mean radiation energy density in the system, it increases steadily as the radiation passes through the entire domain until it reaches the light crossing time, at which point that the increase in the radiation energy density increases much more slowly until reaching some saturated state where in the bottom panel showing the total temperature of the system, the system reaches some thermal equilibrium, at which point we can produce snapshots here showing, for example, a lower and higher angular resolution. And again, we find, as a result of this effect from the discretization, that you'll end up with these colder regions above and below the midplane that we don't find in a higher angular resolution. But it also means that the midplane of the disk can get much lower, as we expect, given the more rays that are more parallel to the radial direction. And before we proceed to a fully hydrodynamic simulation, we can actually do a hydrostatic comparison with a radiative Monte Carlo radiative transfer code such as RAD-MC3D. And so we can see here in this top panel the midplane temperature profile as a function of distance. While we have good agreement before reaching higher optical depths, once we pass that, our Athena++ results can diverge from this ray tracing solution as much as 30% or a factor of 2 at the far back end in the midplane, again, depending on the angular resolution that we use. And in this bottom plot, it's a similar temperature profile, but this time in terms of the optical depth. And as we see that we have agreement up until about optical depth of unity, at which point the temperatures, as we expect, to drop off significantly. But again, some disagreement there because of the angular resolution. So as far as future work goes, I am currently extending this module to allow an odd number of polar angles, which would include a coplanar set in that radial direction, which should hopefully give better results against, for example, the radiative Monte Carlo solutions. And then once satisfied there, we will introduce frequency-dependent absorption and scattering tables of the dust, as constrained by recent observations of protoplanetary disks. And then finally, do the full radiation hydrodynamic simulations, for example, to study the effect of a non-vertically isothermal disk on something called the vertical shear instability, which naturally arises from the angular velocity gradient in the vertical direction, since the surface layers of the disk will rotate slower than those at the midplane, which leads to turbulence and thereby affecting various aspects of planet formation. And so with that, I will end it there and take any questions. Thank you very much for your time. Thank you very much, Danny. Oh, yeah. You're gonna do, yeah, go ahead. Doug.
Do you use this? Yeah. Thanks. This was really cool.
Thank you.
In one of your plots,
Yes.
I think it was you showing the optical depth. I keep going back a little bit. Yeah, like here, or the one previous to this also.
Yeah.
Yeah, there's like this weird like shadow thing at the bottom.
Yes.
What is that?
So we're still investigating that. So we noticed that, yes, in the instances where, for example, it's more egregious in the lower angular resolution, we find like almost like a second penumbra, but it's only at the lower boundary and not at the top. Our first attempts at addressing this was to look at different boundary conditions. For example, whether we use periodic or reflecting to see if that addresses this issue in the polar direction, but it doesn't seem to be a result of that. So now our next suspicion is it might be actually to do with the radial boundary conditions. It might be just some, not quirk in the code, but because it's only happening on one end and not the other, we suspect it's what the ghost cell is doing in terms of shooting out these rays. Basically, there's no downward coming ray from the other pole that's being picked up there. So it is a little thing that we're currently investigating.
Okay, thank you.
Yeah. Jordy? Yeah, Jordy.
Yeah. I had a question about your initial conditions. Like
Okay.
you said that you added like the sigmoid because
Yes.
of like, numerical reasons. But can you also make an argument from physical reasons why it should go down? Or is this like...
Why we should have like...
Like it goes down, right? Why would it go down in a real...
Oh, why would the density decrease?
No, on the other side. You're like
over
dropping
here.
it, right? To avoid the sharp jump in extinction, or at least that's how I understood it.
Yeah, no, yeah. So the initial motivation was mostly, to address numerical issues.
Because if the density would have been higher, your opacity close in would have been different, and your temperature in the disk far away would also be different, right?
That's true. Yeah.
So.
Yeah. Because we're starting this already at 10 AU in the disk, that's like roughly where Saturn might be, and so there's a lot of disk beyond this. So physically, you wouldn't find this kind of density profile at the midplane, but that is something as we iterate to develop our fiducial model that we'll end up with. We probably will go back to something of a more realistic disk profile. But as we're doing the development process, we didn't want to get bogged down with any kind of numerical artifacts this early in the game. And so once we're satisfied with the convergence, especially comparing against Monte Carlo methods, then we'll go back to a more realistic disk model for sure.
Maybe you can. I don't know how the extinction coefficient exactly works in your case, but maybe more like a flatter density profile, maybe.
Yeah,
keep things more constant instead of. Sharply decreasing by 2 orders of magnitude.
Yeah, that's fair. Yeah, absolutely. Thanks for the feedback. Yeah.
Thanks, Stanley. Again, please. Next up, we have Tanay Bandarkar. Congratulations. Thank you.
Nope, that's also there we go. Can everyone hear me? Good. So for those who don't know me, my name is Tanay. I am primarily a PhD student at the University of Pennsylvania, where for the past 5 years or so, I've worked on the development of the hardware for the Simons Observatory. So many of you are probably acutely familiar with what the Simons Observatory is, and I hope to tell you much more detail what we actually do with it. But here we have a picture of the Simons Observatory site as of, I think, last summer, August or so, and you can see one of the telescopes, a large aperture telescope, which is the one I focused on mostly for instrument work, and then 3 small aperture telescopes over there. And I'll get into the details between the difference between the 2 telescopes and their respective science goals in a second. But obviously here at the CCA, I can't do much hardware work. There's not the room for that. So I have shifted from working on the hardware for the Simons Observatory to the software side of things. So how do we get meaningful detector data and translate it to useful cosmological science? And I figured the best way to start this talk is to sort of discuss why we are studying what the scientific motivation behind the Simons Observatory is. And this is a talk in cosmology, so I'm almost legally obligated to show a diagram like this. But it's a very useful diagram in explaining how we think about the universe through our cosmological observations. So the right way to read this diagram is time is your x-axis. As an observer, you'd be over here. And most modern cosmology theories consider the universe starting with something like a Big Bang and going through a period of rapid early universe inflation. And in that period of rapid inflation, the universe is very dense, it's very hot, it's very messy. But any interactives that produce light will produce light that just rebounds off particles nearby. And this is sort of the case for the first 380,000 years of our universe's history. But as the universe cools and expands, it gets to this point where light can finally freely travel without hitting something else. And that last scattering surface is what we now know as the CMB, the cosmic microwave background. And it's been the subject of decades of observations. Going back to the 60s, we had the initial discovery out in New Jersey at Bell Labs. And then we've had several generations of space-based missions, COBE, WMAP, Planck, making improved precision measurements of the CMB. So the CMB is really our only window into this early universe, and there's a lot of interesting and exciting physics going on here, but we can't do anything aside from observing the CMB light to actually derive what's going on. And then you'll notice light from the CMB has to travel all the way across the universe to reach our telescopes, which means it has to interact with everything in the history of the universe. So light from the CMB can also be a useful tracer for the development of large-scale structure, among other things in the late universe for cosmologists. So the point of this slide is basically I want to show that there's 2 main science goals that we can sort of derive from the CMB. One is early universe physics, and one is late universe physics, where late is after 380,000 years. OK. So as I mentioned, I work with the Simons Observatory. Many of you are probably familiar with it. ESO is a multinational collaboration with over 300 people in it who work on things like hardware, software, analysis theory across the world. And ESO consists of 7 telescopes. 6 of them will be the small aperture telescopes, which I showed 3 of in that picture before, and 1 is the large aperture telescope, which I'll focus on today. If you've seen a slide or something like this about ESO before, you'll notice that this number has gone up from 3 SATs to 6. That's because we've had funding secured by our UK and Japanese and UK collaborators to build 3 more sats. And of course, that also improves our sensitivity since we'll have more detectors on sky. OK, so what are the science goals for ESO, and how do they fit with the SAT and the LAT? What does that dichotomy mean? Well, the SAT is focusing on making large angular scale measurements of the sky, particularly of the polarization background of the CMB. So for decades now, the measurement of B-mode polarization through the tensor-to-scalar ratio R has sort of been a holy grail science result from CMB experiments. This measurement would give smoking gun evidence of early universe inflation and could potentially be Nobel Prize-worthy winning. A few years ago, you may remember the BISOP2 collaboration claimed to have made this measurement, but it was shown that the measurement was actually obscured by foreground dust. So this is a really difficult measurement to make. You need very good sensitivity and a very good understanding of systematics. Hopefully, ESO can solve those problems when they come online. The Large Aperture Telescope focuses on small angular scale sciences. Now, this is less singular as compared to the SATs, but we can derive a lot of interesting cosmology from the measurements made by the LAT. So this is a table from our forecast paper, which is now about 5 years old. It highlights all the important parameters we're expecting to draw from our observations. So here you can see R, that's our scalar to tensor ratio. But then you can see a slew of other measurements that the LAT will especially be focused on making. So measurements of the power spectra, measurements of the neutrino mass and number of relativistic species in the early universe, and then maybe most importantly to the people in this room, measurements of lambda CDM, pertaining to lambda CDM, including sigma 8 and H dot, which we know now is in significant tension. So I also just want to highlight what SO is actually bringing to the table. So this was the current 5 years ago. This might be updated now. What the uncertainties are on the parameters that were being measured at the time. And you can see just to the baseline level, there's an order of magnitude and increase in the certainty of those measurements, which is obviously a very significant change and potentially important to the development of modern cosmology, including theories like lambda CDM. And then, of course, the goal is to fully, if we are fully functioning and working great, an even higher increase in understanding. OK, so if you've always wondered what I look like, oxygen deprived and 6 weeks in Chile, today's your lucky day. That is what the point of this slide is. This is me February last year when we were closing up the receiver that sits in the Large Aperture Telescope. This is the camera that will be collecting all the information. This was about a year ago. And then when I went back to Chile in August of 2023, and this is what the status of the telescope was at this site. So this camera here gets set up in this receiver cabinet up here. You'll look at this telescope, and you'll notice that there's something missing. And those components are the mirrors. Those components tend to be very important to us if we want to make measurements of the CMB. You can't really do that without mirrors. So right now, we're in a holding pattern, waiting for the mirrors to be developed. So what do we do in the meantime? How can we get ready to get these measurements that will be coming in from the LAT so that we can produce science-ready data for the community? So we're going to get tons and tons of raw detector data. There's going to be an order, and I'll show this in a minute, an order of magnitude increase in the number of detectors on sky from SO based on ACT and BICEP2 and South Pole telescope numbers. How do we get that raw detector data into useful cosmological measurements? And that's what I've been focusing on here at the CCA. So this is going to be an unprecedented amount of detectors. We're expecting to field over 100,000 detectors in this CMB experiment. Current experiments like ACT, for example, have orders of close to 10,000. So we're seeing an order of magnitude increase. And while many of the techniques that we use in ACT for cleaning data will be relevant here, we can't do what ACT did. So ACT obviously spent a lot of time looking at things at hand. We have to automate it. There's just 120,000 time streams that's impossible for humans to look through unless we hire a bunch of undergrads. So the point of the SO data pipeline is to automate all of that and make sure it's done effectively and efficiently. So this plot here, these are raw detector time streams from the LATR, from the receiver I was standing in front of. And this is really messy. This isn't even looking at the sky. This is actually pretty dormant. This has to become this CMB map here or something like it. You can see point sources. You can see structure in the CMB. You can see clusters, which are circled here. How do you go from this to that? And that's sort of been the focus of what I've been doing here. So we have decided to employ this very complicated but comprehensive data pipeline that should deliver data products from those raw TODs. So we're expecting thousands upon thousands of TODs. How do you get that data from Chile to North America? Well, right now, it gets recorded on hard drives in Chile. Somebody puts it in their backpack and flies up to North America, where then is rsync here. That's very ineffective, or inefficient, I should say. Eventually, there's going to be a fiber link so that data that is immediately streamed will be rsynced up to North America. OK, now you have data in North America. What do you do with it? Well, I showed you earlier that it's very messy data. We have to start cleaning it. Data from the raw data from the detectors are messy. There's going to be glitches. There's going to be trends and common modes that we have to remove based on how the telescope scans and understanding based on instrument systematics. Understanding those systematics and removing them are a key important feature of this data pipeline. And of course, we have to understand what our detectors are actually seeing and understand what they're calibrated to. And all of that will be informed within this data pipeline. So this is actually data from the ACT telescope run through the SO pipeline. So you can see we actually find glitches. The next step is to remove the glitches and fill them with something that actually looks realistic. OK, we've cleaned our data. The data looks great. Now what? Well, we have to start producing data-ready products. Otherwise, the scientific community doesn't really care what we're doing. So I think the easiest and most important product that we'll produce are maps. SO and ACT and other collaborations use a maximum likelihood map maker, which relies on conjugate gradient solver, to produce maps such as this. So these are maps actually produced using simulated CMB data here at the CCA. And you can see that these maps will be eventually translated or derived. I should say you should derive power spectra from these maps. And then using that sort of information, you can start deriving cosmological parameters, like I mentioned in that earlier slide. And I also want to point out that, as I showed in one of the earlier slides, there's going to be other things than the CMB in our map. So we'll have point sources, hopefully transient sources, and clusters. And SO will share a considerable amount of sky with other surveys like LSST, DESI, X-ray collaborations. And doing cross-correlation and cross-matching between our observations and their observations, I think, could be potentially very powerful in astrophysics and hopefully a science goal that we can meet within the next few years. OK, and I wanted to show this slide in particular because this is what I've been thinking about for the last couple of weeks. As I mentioned earlier, there are point sources in the sky. We have to figure out a way to detect them and then subtract them from the maps. So we use a point source finder that relies on a match filter. This is something Act has in the past, but it isn't perfect yet. So you can see it finds point sources, then it finds something that's not really a point source. And this is actually because this point source is just super bright compared to everything else in the sky. It gets a little confused here. And then the edges of the map are going to be very tricky for us to deal with too. These are clearly not all point sources. We have to figure out ways to trim those point sources out, most likely through masking methods, so that the collaboration doesn't think these are point sources and report them dubiously to the scientific community. OK, so let's look ahead. What's coming up? So as of now, the LAT mirrors will be installed in June of 2024, July 2024. It keeps getting pushed, which means first light in late 2024. It'll go through a period of early instrument commissioning before we can start producing science data. I do want to point out that the first of the sats has achieved first light, which is very exciting, and it's currently going through the commissioning period that I just mentioned for the LAT. In the meantime, we're going to keep testing the pipeline. We're going to make sure that the pipeline is as ready to go as possible before we turn on the telescope. And we're going to do that through the use of simulations. So here I have taken simulations and run the SO map maximum likelihood map maker plus other elements of the pipeline through it. And you can see it's not quite perfect yet. There's some strange striping going on in the maps. That's not expected. We think that's because of our treatment of the atmosphere in the simulation. So the atmosphere is actually very dominant in CMB observations. We have to figure out ways to treat that properly and then start actually doing analysis on that. So for the next couple of weeks, I'm hoping to finalize those simulations and understand what we're doing in the atmosphere. And then the pipeline is also going to lay the groundwork for future collaboration. So CMB-S4 will obviously be also interested in this sort of stuff. We hope that our pipeline will inform theirs. So I just want to wrap this up by thanking everyone who helped me here. So I want to thank Simone, Matthew Hasselfield, Audrey, who are all local SO people, but have been there to support me throughout this entire project, answering my many questions. Of course, the entire greater CCA community, the FRFs and the staff here who answered all my scientific and non-scientific questions. And then finally, least but most important, the pre-doc, last but most important, the pre-doc cohort who kept me sane, although now debatably not so, through this entire process with the endless outings and the numerous puzzles we've been solving in the pre-doc office. And with that, I am happy to answer any questions.
So you showed that streaking in the simulation data.
This one.
Yeah, that's simulation, right?
Yeah.
Was the previous slide also simulation data with streaking? Because I was very confused. No,
like
keep going. I think it's like previous to this even.
This one.
Yeah, is that also simulation
Yeah, so this is
data?
all of this is simulated data, and
I
you
thought it
see
was
the
like
streaking
observed.
going through it too. It's sort of being obscured because of our lack of understanding of the atmosphere. So when we were crafting the atmospheric realization for this, there's two components. One was there because we thought it was accurate. The second one was there because it made us happy, and we need to figure out a way to objectively make ourselves happy.
Right. Can I ask another question? Is that? Do you think lambda CDM is wrong? Why or why not?
Oh my gosh, are you really asking me this right now? I think there's room for improvement, right? There's lots of tensions in it. I'm not going to say who I think is wrong and who I think is right now. Okay. But I think making better, more precise measurements of those sigma 8 H0 are really the only way to determine whether lambda CDM is actually a really realistic model of cosmology.
It's an excellent political answer. Thank you so much.
Yeah, Case.
When you say you have glitches and all this post-processing and masking, all that, so are they done separately on steps? Like, do you not accumulate systematic people looking into like joints modeling of like the whole data stream?
Yeah, so they are done step by step. So you'll do glitch finding first, and you'll gap fill those glitches. You'll do detrending, so on and so forth. We have part of our pipeline is just treating this sort of low-level systematic stuff step by step, so that we can get cleaner TODs before we get to the map making and point source detection.
Right, and the second part of the question is like, well, I mean, fundamentally that will introduce bias, right? Because they're not accounting for correlation between steps.
Yeah.
So are there efforts that like, wait, let's take the whole pipeline and jointly model them at the same time?
Yeah, so I think each one of those steps, like the gap filling and all that, those are developed individually. Part of my job here is to sort of comprehensively run the TODs through the entire pipeline and make sure it makes sense on the other end.
So I had a question for you. As someone who studies galaxy formation, I was looking at your parameter table, and I saw there was 2 galaxy evolution parameters. So I was curious if you could say a little bit about what those mean.
I'm actually the least familiar with these 2 parameters, which is why I did not mention them in my talk.
Totally
but
fair.
I'd be happy to look into this and talk to you about it later.
Yeah, I would like to know what are the 2 key parameters that tell me all about galaxy evolution. So
we should do some research, and I'll talk to you later
Cool,
about
thanks.
it.
All right. Let's thank Tanay again, please.
Thank you.
All right, next up we have Katie Chorowski. There you
so
go.
much.
Congratulations, Katie. It's been great having you here.
Thank you. Cool. All right. Hi, everyone. My name's Katie. I'm a pre-doc here working with Chris and Rachel Cochran, who has an appointment at Columbia. I want to take a second to thank everyone for being here, as well as for everyone involved in the pre-doc program. It's been really wonderful to be able to spend some time here and do the research. So my talk today and my research project here is primarily motivated by observational studies. So I'm at UT Austin working with Steve Finkelstein in galaxy evolution. And my work is primarily focused on this class of galaxies called massive quiescent galaxies. And I hope to kind of talk you through why they're interesting and what my work here does for them. So since I'm an observer, I'm going to start with an observer's view. When we look at the sky, what do galaxies look like? I know the audience is broad, so for some people this might be just like really silly review, but I hope that this will put a little context for those who don't work on this. But when we look at the sky, really we kind of see galaxies that look all sorts of ways, but we can really classify most of them in these two distinct. You have your beautiful spirals, like these are the galaxies that the Milky Way is, that you see mostly pictures of. They're typically star forming, they're younger, they're bluer in color. And then you have this other population that perhaps are less exciting via photo, but they're typically older galaxies. They're redder in color, and they host a lot of older stellar populations. So a lot of people here do galaxy formation modeling, and so we can start to ask us, how can we reproduce these galaxies via modeling or our simulations? And so when we look at forming galaxies in simulations, particularly massive galaxies, we know that if we don't put in any feedback processes, our galaxies just keep forming stars. So in fact, that in the absence of feedback, all massive galaxies should be star forming. Now, I just told you that this isn't the case when we look at the sky. So something happens to our galaxies that instead reproduce the secondary population of quiescent galaxies. And many simulators have already known this, but there are a few primary feedback processes that operate on different mass scales and time scales. And these can be mergers, they can be stellar feedback, they can be AGN feedback, which heats up surrounding gas to stop star formation or expels gas. So my population of galaxies I'm most interested in, these massive quiescent galaxies, the one that's all the way in the bottom right there, are really very interesting places to study these, because these are galaxies that have undergone extreme amounts of star formation, but also shut down their star formation. So they have undergone these feedback processes that we talked about. So they provide this great place to study, what those might look like, and we can sample them in the sky or look for them in the sky, and then go back to our simulations to see if we can match what we see in the sky. So here, that's all fine and dandy. So we know that right now, if we just look at the sky, all the local galaxies, all the local massive galaxies are actually quiescent. This number changes as we go back in time. Around redshift for two or so, half of massive galaxies are quiescent, and the other half is star forming. Now, what's really interesting is as you go up to higher redshifts, for example in this plot, redshifts above 3, we have a really hard time predicting massive quiescent galaxies in simulations typically. And this is also where we're starting to really push our observational ability to find these galaxies. So currently, the most high redshift massive quiescent galaxy found is a redshift 4.6 galaxy with stellar mass of 5 × 10⁻10, I believe. And so this galaxy, in the 1 and so billion years that the universe has been alive, has formed extreme amounts of stellar mass, but also shut down that stellar mass. So observationally, we're really pushing what redshift we can find these galaxies, but if you notice these points on the right, they're a little bit all over the place, and the error bars are large. This is due to a few reasons. When you go back in time, these are harder to find. They're a little rare, so our sample sizes are very small. But also, in extragalactic studies, we really don't have many large area surveys to look for these galaxies. So we suffer a lot from cosmic variance errors or the field-to-field variance as we look at in the sky. So part of my graduate work is to do this study of massive quiescent galaxies and the Sheila survey, the Spitzer-Hethix Exploratory Large Area Survey, which is a 24 degrees squared field, which is very large in terms of extragalactic studies. It has coverage from the UV to mid-IR, and compared to previous works that have done similar things, it reduces the error of cosmic variance by about an order of magnitude compared to UltraVista, which is one of the big searches that have been done before. And so now that we have a data set, what can we do to select these galaxies? There's really two primary ways that these have been selected. One is based on its color. So as I said before, these galaxies are red, so you can plot them in their rest frame UVJ color diagram. A large U minus V is designed to recover a strong Balmer break, and a relatively flat V minus J is designed to limit dust contamination, which can masquerade as a strong Balmer break, and I'll talk about that in a little bit as well. And so this is a great way of looking for these galaxies because you really need just three things about this galaxy, these three colors. However, it's really struggles a little bit with contamination as well as it doesn't translate very well to high redshift. So this works very well in very low redshifts, in my world meaning less than 2. But as we push to higher redshifts, this becomes less clear. The other way to do this is with SED fitting. So SED fitting is a way where we observers with photometric information that we have available to understand what that galaxy looks like in terms of its physical properties. So we take photometric information, we then fit different stellar populations to the photometry, assuming different dust laws, ionization parameters, and so on, and that allows us to get stellar masses, star formation rates, and other physical properties. So that all sounds pretty straightforward, but there is this one problem that I kind of alluded to, that massive quiescent galaxies are red, and there's another population of galaxies that are often very red as well, and those are dusty star-forming galaxies. So these are galaxies that are very star-forming, so they're not quiescent, but they have large amounts of dust, which attenuates light in the UV to near IR and then re-radiates it at longer wavelengths. So this is an example of a real galaxy. The black points are the photometric points. And then the red line is an SED fit to a quiescent galaxy, so it fits the black points really well. But you also have these two blue lines, which are a very different type of galaxy that also kind of follow the lines fairly well. And so this is one of the primary reasons why I started the project here, is to really understand whether or not when we select galaxies that we say are quiescent, how well we're really doing in determining that. So to do that, we can look at simulations. Simulations, we know the truth, so that's a really nice place to start. And we can look at how well we can recover these physical properties based on, the information that observers have. So we're using TNG 300 mainly because this is a very large volume simulation, which is required if we want to pick out these rare sources. We pick all galaxies with stellar masses greater than 10 to 10.5 at redshift ranges of 3 to 5. And with those galaxies, we can perform radiative transverse skirt to get a synthetic SED, so the figure on the right there. From the synthetic SED, we can then generate some mock photometry. So this can be done. It's done here for Sheila, but this can be done for any survey of your choice. And from the mock photometry, we then go back and refit based on our SED fitting codes. And from that, we then have physical properties. From our estimated physical properties, since we're working with simulations, we know the truth. We can then use that to recover, to see how well we're recovering the physical properties. So this is when an observer looks at a galaxy and they say they're measuring X stellar mass, X star formation rate, how well is that compared to the real truth? And so on the left here, I have the stellar mass. On the x-axis is all the true from the from TNG 300, and y is recovered. And so the stellar masses do fairly well. The shaded region is just a half a dex. That's fairly well, I guess, in terms of observer space for me. There is kind of an interesting population of galaxies that have an overestimated stellar mass, and those are all galaxies with low specific star formation rate, or quiescent galaxies, which is kind of interesting. The plot on the right is the star formation rate recovery. And again, most of them are recovered fairly well, but the population that we're most interested in looking at are the sources in the bottom right region of the plot. Basically, these are all galaxies that our SED fittings say are quiescent, but aren't in fact quiescent. So we looked into that a little bit and basically looked at what might be causing this. And we find that we can plot this against the dust attenuation and find that the star formation rate recovery is strongly correlated with dust attenuation. And this is perhaps unsurprising, but it's kind of the first time that we've been able to use simulations to do this. So we find that these all have high levels of dust attenuation. And this kind of confirms that we can't really just use, at least for this, the wealth of data that we have in the UV and IR, and perhaps we need something more, such as the WST, MIRI, or ALMA, which probes longer wavelength regions of the SED. Next, we did a color-color diagram, which I've mentioned before, and from this, we're going to look at how well we're selecting the galaxies and how pure they are. Again, we find that the completeness is fairly high, meaning that we're selecting mostly all of our quiescent galaxies, but the purity drops significantly, again, with these dusty sources contaminating the color space. So in the future work, this is really a lot to do with motivating follow-up observations as an observer for these sources. We always want to have reasons to propose for telescope time and to really limit dusty star-forming galaxies. And I'll leave my summary up and take any questions.
Thank you so much, Katie.
Thank you.
Questions? Shoot. Questions? Doug.
It's a great talk. Did you figure out why that those star formation rates were overestimated at all in that one plot, like that population? Yeah.
These? Those?
No, those ones at the top.
The masses?
Yeah.
No.
No, you didn't figure that
No.
out? Okay.
Yeah.
That's interesting. Thanks.
I'm curious, what's the hard edge on the left there from?
Just the selection. So this is the true, so we just select everything greater than 10 to the 10.5. Yeah.
Jordy?
Yeah, great talk. I had a question about your last part about like going, for example, to ALMA.
Yeah.
Would you expect that there are other emission mechanisms that might drain out your signal that you're actually looking for? Like if you're measuring at, say, ALMA millimeter waveband, this is radio. Mm-hmm. Like, for example, the supermassive black hole in that galaxy might have a stronger component? Or do you think that this signal will be the strongest signal at that frequency?
Sure, yeah. I guess in terms of the galaxies that we expect as contaminants, like ALMA will be able to clearly tell us like whether or not. But I guess there's also a lot of recent JWST observations are finding like quiescent galaxies also host like active or supermassive black holes. So in terms of that, I'm not sure like whether or not ALMA will be able to distinctly tell us between those two cases.
Okay, let's go ahead and thank Katie again. Next up we have Trump.
Okay.
Congratulations.
Thank you. I'll be the first one to take water. Okay. Hello, everyone. My name is Trung Ha. Before I get started, I would like to say thank you to my supervisor, Jonas and Jordi. And also, I'd also like to thank Lorenzo, Shirley, and Case, who have spent a decent amount of time helping me with this project. The title of my talk is Awesome Segmentation of Current Sheets in Magnetized Plasma Turbulence, and I will explain to you what awesome means in just a second. Okay, so I want to start with some motivation about why we carry out this project. So we would like to segment and identify and segment current sheets in plasma simulations. And the reason behind that is that, first of all, current sheets are these thin sheet of regions that has very high current density, and they are usually found at the boundaries between the changing of polarity of magnetic field. And this can be found, say, at the dissipation scale of MHD turbulence. And so we find these current sheets in a variety of location in nature. So anywhere from the heliosphere of the solar system all the way down to the accretion flows onto black holes. Okay, so because of how wide we can see these current sheets in the nature, we would like to have a fast and robust method to segment these current sheets. And by being able to segment the current sheets in MHD simulation, we are able to efficiently track the location and the rate of energy dissipation as well as plasma heating in MHD turbulence. We also, by segmenting out these current sheets, we can do statistical study of the morphologies of these sheets and then study their evolutionary history, so how they're formed. Lastly, by isolating these regions of interest, we can quickly analyze the property of the plasma within them. So, for example, if we have a fully kinetic simulation, we have both the field as well as the particle information. And for example, then we can track how much plasma is inflowing into the sheets, as well as whether there is particle acceleration outside of the sheet. Okay, so I would like to also highlight some previous efforts that has been done to identify and segment current sheets. The classical methods is to use a simple thresholding method. So, for example, if you have a map of the current density, you can calculate the RMS value of the parallel component of the current density, and then you can take a threshold of anywhere from 2 to 3 times the RMS value and say that anything above that is part of a current sheet. Or alternatively, more recently, Busov and Natila 2021 use a more sophisticated method by integrating more than one feature into a machine learning model using statistically ensemble method to identify current sheets in 2D simulation. And the main goal that we started out with this project is that we would like to generalize this method into to apply them to 3D simulations. Okay, so the machine learning method that we use for this project is called a self-organizing maps, or SOM. And SOM is an unsupervised machine learning technique, and we need to use an unsupervised technique because there is no ground truth to our question. So we don't have a rigorous definition of what a current sheet is. So at the same time as trying to identify, to track them, we also would like to understand what current sheets are. SOM is usually used in anomaly detection, most specifically in the financial sector, but it can also be used to represent a high-dimensional input data onto a lower dimensional, usually a 2D neuron grid. And it has two key advantages over k-means clustering, which is, first of all, is that it is a nonlinear clustering method, and also that it's able to preserve the topographical structure of the data. So on the right-hand side here, you can see an example of a 2D SOM map trying to fit onto a naturally occurring cluster that possibly is in higher dimension. And the way it does that is that it finds the closest neuron to a data point, and it moves the neuron closer to that point. So when the neuron is moved closer, it also consequently drags other neurons in the neighborhood to that, stretching out the map and conforming the map onto the structure of the input data. Okay, so we apply this SOM method on a variety of plasma simulations. We have three input, we have three training data. We have a Harris current sheet simulation, which is the ideal case of just two magnetic field moving in opposite direction and one sheet forming at the interface. We also have a decaying turbulence box and as well as a driven turbulence box simulation. And we have 6 total features that we feed into this SOM. So it's the parallel and perpendicular components of the current density, magnetic field, and electric field. And by parallel and perpendicular, I mean parallel and perpendicular to the direction of the magnetic field. And then after we have finished training, we can map each cell in the simulation back to the nearest neuron, which then we can assign a cluster to that cell. Okay, so, now awesome. Why do we call it awesome? Well, this is an improved Python library for SOM, and this is, I rewrote the PopSum library, which was previously written by Yuan in 2018. Although PopSum has most of the functionality that we would need for this project, it was originally written for a much smaller input data. So this can run for maybe 1,000 data points, but for our simulation, we have up to hundreds of millions of data points due to the 3D nature of the set. So this was written for one core, one CPU core, and very unoptimized. So I have optimized for speed by converting some of the list operation into matrix operations. I've also changed wherever possible from Panda data frames to just NumPy arrays. And also, I accelerated the training with Numba, which is a Python package that automatically allow for parallelization of for loops, and as well as a just-in-time compiler to speed up computation. And all of that combined give a significant speed up of Awesome compared to PopSum of in the order of 100 times. Okay, so what are the results that we have from this experiment? So in this plot here, you are seeing a JPAR plot with a threshold of 2 times the RMS value, and then each of these panels following that is a different realization of the SOM with slightly different input parameter. And you can see that for each of these plots, there is always one cluster that traces out what we would expect a current sheet would look like. And it traces out really well. However, the slight problem with that is that they don't always match up with each other. And because you can see that each of these cluster has a different color, meaning that the SOM is assigning it a different cluster every time. So how do we fix this problem? How do we generate a more robust clustering result? And well, we can do that via a statistically combined ensemble. So statistically combined ensemble is a method that was developed by Busov and Attila, and they do that by running multiple realization of the SOM with slightly different parameter and then stacking them on top of each other. By stacking them, you get a general signal strength of each of the cluster, and then from that signal strength, you can get the final clustering results. So this is the result of doing this SEE. I also want to mention that by doing this SEE, I have also learned how to use JAX, and that's allowed me to do GPU accelerated in terms of this SEE, and that's also provide another 100 times speed up compared to the original. So for the SEE, if you look at cluster 1 here, it matches up surprisingly well with JPAR. And on the right-hand side is the volume rendering of that. So the yellow part is the SEE result, while the blue and red part is the parallel component of the current density. And lastly, I would like to show another result, which is the same technique, but apply on the decaying turbulence box simulation. And in this case, the result is less clear. However, if you look at cluster 4, you still see some, or most of the sheet-like structure that a thresholding JPAR would give. And that is also a volume rendering, but it's much less clear because there's a lot more structure going on in this case. Okay, so lastly, let me talk about what we want to do in our next steps. So we want to continue investigating the physical meaning of these SOM results. So as you might recall, there's more than just one cluster in the SEE. So we would like to investigate whether any of those clusters has more physical meaning than just the one we identify as the current sheets. Then we would like to write up the science paper and submit it to a journal. And lastly, because awesome is so awesome, we would like to polish up that package and publish it in the journal for open software. And I'll leave my summary slide up, and thank you all for listening.
Thank you so much.
I don't remember whether I asked you this before, but like, does the SOM support creation or delete of the node? Like, so you have a map, you initialize a grid, and you can drag the grid around and all that. But does it support like creation and delete of a node or not?
No, it doesn't.
I see. So
Yeah.
let's
So you
check
have to
out.
specify at the start what is the x and y dimension of the size of your node.
Yeah, let's chat more after then.
Okay.
So when you have like the SEE decaying turbulence, I was just curious, like, how much of the volume is filled with the current sheets, right? Because like the thresholding method, I think Vladimir used, he gets like 1% of the volume is the current sheets. Like, do you get?
I think this is if I recall correctly, the volume filling fraction is about 3% for the, So I found that it fill up a higher volume than 3 RMS value.
Is it possible that the velocity field could also give interesting extra information for identifying the current sheets?
Yeah, I believe so. So right now, we only use the field that are readily available. I think we could consider using V, but I'm not sure that all of our training data has the V field.
Do you have any way to measure like how wrong you might be? Because there's like you train it on like this a couple of cases or something, but then you go here and you have like tons of current sheets.
Yeah.
And you're not going to check them each one by one. So how do you have some kind of measure?
Right.
Of how wrong it
So
might be?
I can do. So in this case, I have tried to do basically. I can calculate a intersection between the two and also a union, and then so. Built into SEE is a way to do map-to-map, cluster-to-cluster comparison, which uses a quality index. So I think I can just import that part of the code out and uses that to say something about the quality of the fit.
Okay, thank you.